In the first part of the lecture on alpha decay, you have seen some of the important facts regarding the process alpha decay. You have seen how we can calculate the Q value of this process and what amount of this Q value of the process is shared as kinetic energy by the alpha particle and the daughter nucleus. But we have not discussed any proper theory of this alpha decay process. So now we are going to start a proper theory of alpha decay, and this proper theory is known as Gamow's theory of alpha decay. In fact, in this first part on Gamow's theory of alpha decay, we will not see any proper theory regarding this alpha decay, but we will only discuss some of the introductory facts regarding the theory of alpha decay. It means we will mainly discuss how we can say that the classical mechanics is unable to explain this process of alpha decay. Only this process can be explained in terms of quantum mechanics. In fact, by quantum mechanical theory, three scientists explained the alpha decay process. So first of all, you have to see that after the discovery of radioactivity and the emission of alpha particle raises a simple question, and that question was, why do we observe alpha radioactivity and not a proton or deuteron radioactivity? It means in radioactivity it is seen that alpha particle is emitted, but not a proton or a deuteron is emitted in the process of radioactivity. What is the cause behind this? Actually, you can explain this fact with the help of semi-empirical mass formula. You have studied previously the semi-empirical mass formula, and on the basis of this semi-empirical mass formula, we can explain that why in radioactivity alpha radioactivity is observed, but the proton and deuteron radioactivity is not observed. You know, the binding energy of last nucleon is found to fluctuate rapidly with the mass number A, and the nuclide is found to have zero binding energy, and thus they are all stable against nucleon breakup. So no nucleus is actually active for the proton and deuteron decay. The binding energy of alpha decay on the other hand, the binding energy of the alpha particle on the other hand, or you can say the separation energy of alpha particle is found to be comparable with the binding energy of the last nucleon in the case of light nuclei. And the binding energy of alpha particle is found to be negative for the heavy nuclei whose mass number is greater than 150. And that's why we say that the heavy nuclei are unstable for alpha particle breakup. So what I have told you, I am just going to explain it. You can see that the alpha decay process takes place like this. If you consider that there is a parent nucleus X having the charge number or proton number Z and nucleon number A, that is mass number A, if it suffers alpha decay, then we get a daughter nucleus whose atomic number is in fact Z-2 and mass number is A-4, you know. And at the same time, there is an alpha particle which is emitted from this nucleus X, and this alpha particle has been denoted by this 2He4 nucleus. Now the Q value of the alpha decay process, or you can say the total energy which is liberated in this alpha decay process, you know, this is simply equal to the mass energy equivalence of the difference of the mass of the parent nucleus and the products. So you can see the Q value of the process is what? This is mass of the parent nucleus ZXA minus mass of the daughter nucleus, that is m of Z minus 2 dA minus 4, minus mass of the alpha particle, that is m of 2He4 times C square. Okay. Now you know minus m 2He4C square minus m 2He4C square. This is simply the binding energy of alpha particle. With negative sign, it represents the binding energy of alpha particle. So for the last term, we have written here B alpha. It means this is binding energy of alpha particle, and minus m Z minus 2 dA4 times C square. This represents the binding energy of the daughter nucleus, and that I have represented here B of Z minus 2A minus 4, and m of ZXA times C square. This is equal to the negative of the binding energy of the parent nucleus. So this is minus B of ZA. Okay. Now the difference of the binding energy of the daughter nucleus minus that is B of Z minus 2A minus 4 minus B of ZA. This I have written delta B. This is actually the difference of the binding energy of the daughter nucleus and the parent nucleus. So the Q value of the process can be equated to B of alpha, that is binding energy of alpha particle, plus this change in binding energy delta B. Okay. Now you can see that this finite difference B of Z minus 2A minus 4 minus B of Z minus A, this is well approximated by the corresponding derivatives with dz equal to minus 2, because you can see the Z of the parent nucleus was Z and that of the daughter nucleus was Z minus 2. So what will be the change in Z? This will be Z minus 2 minus Z, and that will be equal to minus 2. So you can approximately say that the change in Z, that is dz, is equal to minus 2. And similarly, the mass number of the parent nucleus was A and that of the daughter nucleus was A minus 4. So what will be the change? Change will be A minus 4 minus A, and that will be equal to minus 4. So you can write the change in A is equal to minus 4. And so in terms of this, you can write this change in binding energy, that is delta B. We can write this is minus 2 del B by del Z minus 4 del B by del A. Okay. Now the experiment says that the binding energy of alpha particle is 28.3 mega electron volt. You can calculate it. So when we will apply the semi-empirical mass formula, you have studied this semi-empirical mass formula, I have written it here directly. So using the expression for the semi-empirical mass formula, the Q value of the process will be what? You can see the Q value of the process is what? This is B of alpha plus delta B. And so substituting the value of delta B and B of alpha, you will get Q equal to 28.3. This is binding energy of the alpha particle, and this much. I am not reading these terms. You can see these are the terms which arise in the expression for the binding energy in semi-empirical mass formula. Actually, when you will put the numerical values of all the quantities appearing in this equation 3, then it is found that the Q value of the process is greater than 0, that is positive, only when A is greater than 150. It means substituting the numerical values, you will get that the Q value of the process is is greater than 0, but only when A is greater than 150. And you know, if the Q value of a process is positive, that process is energetically favorable. It means alpha emission will take place if A is greater than 150. So this semi-empirical mass formula actually supports that there may be alpha decay, but only when the mass number of the parent nucleus will be greater than 150. So finally we conclude on the basis of this semi-empirical mass formula that the nuclei having mass number greater than 150 are alpha unstable, because for those nuclei the Q value of the process is positive, and positive Q value refers instability, and so such nuclei suffer alpha decay radioactivity. Okay, so I hope you have understand that our semi-empirical mass formula also infers that alpha decay process will take place, but only in case of all those nuclei whose mass number is greater than 150. Now we are going to see what is the problem behind this alpha decay process. How this process will be explained, we are going to discuss it. And for this, first of all, let us consider the famous experiment performed by Rutherford, which is called alpha scattering experiment. Definitely you have studied this experiment done by Rutherford and his students Geiger and Marsden. And you know, in this alpha scattering experiment, from a radioactive source, the energetically emitted alpha particles are incident on a heavy nucleus. You can see this figure. I have denoted that this is a heavy nucleus, and from a radioactive source the alpha particles emitted are aimed to heat this nucleus. As the experiment says that this alpha particle and the nucleus are far separated, then there will be no interaction between them. But as the alpha particle approaches towards the nucleus, Coulombian force acts between them, because alpha particle is positively charged and nucleus is also positively charged. So there will be a Coulombian repulsion acting between the alpha particle and the nucleus. Although the actual interaction between the alpha particle and the nucleus is not known, but we can guess that there will be actually two interactions. First one will be Coulombian repulsion, and another will be the short range nuclear force, attractive nuclear force. When the alpha particle will be very close to the nucleus, then there may be an attractive interaction between the nucleus and the alpha particle. So as a whole, you can say, we can guess that there is two types of interactions between the nucleus and the alpha particle. The first one is Coulombian repulsion, and the another is short range attractive nuclear force. Now, as the alpha particle will be very close to the nucleus, then only this attractive nuclear force will be effective, because it is a short range force. But if the alpha particle is in fact far apart from the nucleus, this force will be just negligible, or you can say this will vanish. So you can say that due to rapid decline of nuclear forces with distance, alpha particle will experience diminishing attraction near the surface of the nucleus. In fact, when the alpha particle and the nucleus is at a separation r, then you can guess that these two forces will act. But when this R will be equal to capital R, where capital R is actually the nuclear radius. Actually, in that condition, the nuclear force and the force of repulsion between alpha particle and the nucleus balances one another. So I have mentioned here that at R equal to R, the nuclear attraction is balanced by the Coulombian repulsion. So you can say that the internal part of the nucleus is separated from the outer space by a certain potential barrier which prevents alpha particle to penetrate into it. That is the nucleus. Now, what is this preventing potential barrier? What will be the height of this preventing potential barrier which actually prevents the alpha particle to enter into the nucleus? In fact, this height of the potential barrier will be just equal to potential energy of alpha particle at R equal to R. Now you can easily calculate what will be the potential energy of alpha particle when it is just at the surface of the nucleus. You can calculate it. This is just the Coulombian potential energy. You can say, if you consider that this is your parent nucleus having the charge number Z, and from this you get the daughter nucleus. This is parent nucleus and this is daughter nucleus, and its charge number is Z minus 2, and the alpha particle is emitted from it. So when this daughter nucleus and the alpha particle are at a separation R, what will be the potential energy? You know, the expression for potential energy will be what? This is 1 over 4 pi epsilon naught 2e. 2e is the charge of the alpha particle, and the nuclear charge of the daughter nucleus will be Z minus 2 into E and divided by R. And this result holds only when R is greater than R. It means alpha particle is outside of the nucleus. So you can say that the potential energy or the height of potential barrier when the alpha particle is at a separation of R from the daughter nucleus, that is equal to 2 into Z minus 2e square over 4 pi epsilon naught R. Okay. Now you can calculate this height of potential barrier by taking a proper example. Let us take a proper example of uranium nucleus, uranium-238, whose charge number is 92. And if you want to calculate the height of the potential barrier, that is, what will be the value of this potential energy when the alpha particle is just at the surface of the nucleus. You know, when the alpha particle will be just at the surface of the nucleus, this R will be equal to capital R, where capital R is actually the radius of the nucleus. So let us use this formula to calculate the height of this potential barrier in case of uranium-238, V of R. This is your formula. Only I have changed that this small r is now capital R because we have assumed that our alpha particle is just at the surface of the nucleus. But you know, the radius of nucleus, if it is spherical, this is r naught into a to the power 1 by 3. Okay. Now put the numerical values of all the quantities in RHS of this equation. You know, 1 over 4 pi epsilon naught, this is almost equal to 9 into 10 to the power 9 in SI unit, and Z minus 2. Z for uranium is 92, so 92 minus 2 is here, and E square, this will be 1.6 into 10 to the power minus 19 square. And R naught, you know, R naught is 1.2 FM, so this is 1.2 into 10 to the power minus 15 meter. And A for uranium-238 is 238 to the power 1 by 3. When you will actually simplify this result, you will get that V of R is equal to 28 mega electron volt. It means the potential barrier just outside of the nucleus is of the height of 28 mega electron volt. Okay. Now, this is the potential barrier which is just outside of the nucleus. Now we will talk about the interaction inside the nucleus. In fact, inside the nucleus there is only attractive interaction, that is attractive nuclear force. So we can assume that there is a constant potential energy that will be negative because interaction is negative. So you can think that inside the nucleus the potential energy is constant and it is negative. So we assume here that the nucleus is just like a potential well of depth u0 and width r. You can imagine. So inside the nucleus we assume that the potential V of r is equal to minus u0. Minus sign here represents actually the attractive nature of the interaction, and so when r is less or equal to r, then potential is minus u0, and when r will be greater than this capital R, then the potential will be just the Coulomb potential. We can mention it here that this V of R will be equal to what? This will be 2z minus 2 into E square over 4 pi epsilon naught R for R greater than R. Now you can plot this potential in against of R. You can see this figure. Here on this x-axis I have represented the value of a small r, which is separation between the center of the nucleus and the alpha particle, and on this vertical axis I have taken the value of V of r. You can see, as we have seen, that inside the nucleus there will be attractive interaction, and due to that attractive interaction potential energy is fixed, that is constant, and that constant value I have assumed here this is minus u0, but this minus u0 value is up to a distance r equal to r. Okay, and after r equal to r, this potential energy is actually the Coulombian potential energy. This is Coulombian potential energy. Okay, and this is your attractive potential well. Attractive potential well. Now you can join this curve which represents actually the Coulombian potential energy and the attractive potential energy, which is minus u0, by this line r equal to r. Actually this potential well I have assumed here is a simplified version. The actual potential is actually the actual potential is actually generated by a rotation about this v axis, that is a three-dimensional shape. Okay, so you can see that in case of this uranium nucleus, this maximum value of barrier height will be 28 mega electron volt. This value is for uranium. So what you can think about? If you can imagine here that if there is a nucleus of uranium and we project an alpha particle toward this uranium nucleus, this will be penetrate into the nucleus only when its energy is equal to greater or equal to 28 mega electron volt. Yes or no? Because you know there is a potential barrier of height of 28 mega electron volt at the surface of this uranium nucleus. So an alpha particle projected toward this uranium nucleus will penetrate into the nucleus only when its kinetic energy is at least 28 mega electron volt or greater than it, only then. But what is the actual state of affairs? It is found in the process of radioactivity. When alpha particle is emitted, then it is found that the energy of the alpha particle is never greater than 9 electron volt. In fact, the energy of alpha particle is lying between 4 mega electron volt less or equal to Ek, and this is less or equal to 9 mega electron volt. What does it mean? It means it is found that the energy of alpha particle is lying between 4 mega electron volt and 9 mega electron volt. But to penetrate into the nucleus of uranium, at least the energy of alpha particle should be 28 mega electron volt. So, according to classical physics, alpha particle will never penetrate into the nucleus of uranium. This is just a proper example. In fact, in case of other nuclei, the height of the potential barrier is also of this order, 28 mega electron volt, and whatever will be the height of potential barrier, definitely that is greater than 9 mega electron volt. So you can say in general that an alpha particle emitted during the radioactive decay have never energy which is equal to the barrier height. So no alpha particle can penetrate into the nucleus. Just in reverse sense, you can think, if there is an alpha particle inside the nucleus, see here, there is an alpha particle in this potential well, and this is the height of your potential barrier, which is 28 mega electron volt. So to escape from this nucleus, this alpha particle should have at least 28 mega electron volt energy in accordance with the classical mechanics. According to classical mechanics, an alpha particle trapped inside this potential well, that is inside this nucleus, will escape through the potential barrier only when its energy will be greater than 28 mega electron volt. This is actually classical concept. But as this alpha particle has not an energy equal to 28 mega electron volt, actually its energy is much smaller than 28 mega electron volt. So according to classical mechanics, an alpha particle inside the nucleus cannot escape through the nucleus. So alpha decay is not possible according to classical mechanics. But in practice, it is seen that alpha decay takes place. So definitely we can say that our classical physics or classical mechanics is not sufficient, is not able to explain how the alpha particle is escaping from the nucleus. So alpha decay process, in one sentence you can say that the process of alpha decay cannot be explained classically. Classical physics से इसका explanation नहीं हो सकता है. In fact, as I have told you earlier, that as classical mechanics completely fails, badly fails in explaining how this alpha particle which is inside this potential well, whose height is 28 mega electron volt, from this well the alpha particle cannot escape through the surface of the nucleus. So classical physics completely fails. But according to quantum mechanics, there will be a finite probability of transmission of this alpha particle through the surface of the nucleus, and this is actually just the problem of barrier penetration. And on the basis of quantum mechanics, three scientists, first one was Gamow, the second was Condon, and the third one was Gurney, who explained independently on the basis of quantum mechanical theory how this alpha decay process takes place. But we will discuss this proper theory in the forthcoming lecture on this subject, and that is actually called the Gamow's theory of alpha decay. As I have told you earlier, in this lecture, our aim was only to see what was the problem behind the alpha decay. So in nutshell, you can say that a nucleus is just a potential well inside which an alpha particle is trapped, and classical mechanics fail to explain how this alpha particle will be escaped from the potential well. But quantum mechanics finds its explanation, which we will study in the forthcoming lecture.